7 measures of variability, which is how much things spread. There's 3 different measures of variability. There's the range, the standard deviation, and the interquartile range. You should be pretty darn familiar with the range. You know, it's like we've done that before. The range is the distance between the high value and the low value. You just like subtract it, right? You found the range a lot, you know, so that is the range. Standard deviation is going to take us a little while to get used to. We're going to ease into it, right? But standard deviation is a big thing in a stats class, and it's not that hard to understand. The computer's going to do all the calculating for us. We just need to get used to it, but it measures the distance in a distribution from the mean. It's like how far someone is away from the mean, which is like the average. You'll see 2 different symbols for standard deviation. Standard deviation, like right here, this little S sub x. We'll just pronounce it as standard deviation. That's how we'll say it out loud. But they use that when you have a sample. And like a sample is just like you guys. If I was to like try to get information about Hayes High students and I just surveyed you, you are a small group of Hayes High students, right? You are like a sample of that, you know. The population would be if I surveyed every single Hayes High student. They use this Greek letter sigma. If you don't remember that that's called sigma, that's cool. It's just standard deviation. And I'll help you with all that stuff. You're like, what does this symbol mean? It's like, that's the standard deviation, you know. So that's how far you are from the mean. And then the interquartile range, we'll talk about it later today, but we might as well define it right here. It's the distance between the 3rd and the 1st quartiles. And I'm going to guess that you have done that before. You might not remember it, you know. It's like I don't really remember this, but I think you have done it in an Algebra 1 class before. Find the interquartile range. So these are basically our vocab words for today. Let's just kind of dive in and see how they roll. So here's some data about how long people typically spend traveling to work, okay? Well, it really depends on where you live and how far you got to drive and stuff. So these are 20 randomly chosen New Yorkers, right? You know, people who live in New York, or I should say they work in New York. They don't necessarily have to live there. 20 random people, how long it took them to get to work. So they made the dot plot for us already. They say, find the range. Sweet. What's the high? 85. So we'll show a little bit of work here. 85. And what's the low? 5. I think it's easier to read the dot plot on that, you know, than to look through all the data because, yeah, 5 is the low. And you just subtract them. Isn't that range 80 in that case? That is a big old range right there. Some people took 85 minutes to get to work. Some people took just 5. And then here, the homework program will kind of talk about that resistance thing again, you know. The range is not resistant. Maybe if you want to, like, I tried to put key things like shaded in, you know, on your notes, like in the box, like I shaded it in. So the range is not resistant. Like, remember, resistant means if you had some extreme values, some outliers, that's going to, like, change the value. Would you believe that if this guy went away, like if that 85 went away, then the range would drastically change, you know, like the next high is 65 minus 5, you know, so like that would drastically change that. So that's why the range is not resistant, because it depends on the 2 outside guys, right? If one of those changes, that's going to be really, really wild. So the range is not resistant. So here we go. Here's a double dot plot. Not sure if we've ever seen one, but they've got 2 on top of each other. Here they're talking about some machine. You see there's a dot plot up top, machine A and machine B. So the graph illustrates another problem with range. Like, range sometimes is a good measure of variability, but most of the time it's not, because would you believe that these parallel dot plots, that's what's going on here, show the lengths in inches of a sample of 11 nails produced by each of 2 machines, right? So they're producing nails, and it's like how long the nails are. Both distributions are centered at blank millimeters. Like, where's the center of these guys at? How many millimeters? So they have the same center, 70.0 millimeters. And what's the range? Like, isn't the high for machine A 70.2 and the low is 69.8, and there's the same thing on machine B? Like, so wouldn't they have like the same range if you did high minus low? I did the math for you. If you take 70.2 minus 69.8, you get 0.4 millimeters. They got the same range and the same center, right? But which machine, just by looking at it, it's kind of like Kelly's bowling scores and Earl, whoever that other guy's name was, like, which machine looks like it produces nails more accurately, machine A or machine B? Like, which one's more consistent? Like, machine A had a nail of 69.8, 69.9, 69.9, 70.0 times 6 of them, you know. 78.1. Which one gave you the more consistent nails, machine A or machine B? I think so. Doesn't A have a way more consistent thing, in that? So the lengths of the nails made by machine blank clearly vary more from the center than machine blank. So which one has the big variability? I would say machine B is the one that varies more from the center. On this guy, there's 1, 2, 3, 4, 5 of them that actually landed on the center than machine A. So are you kind of okay with that? Range is a way to measure variability, but sometimes it's not the best because you could have the same range and the data on the inside is just completely different. Are you okay with that? All right, let's see what happens here. 9 children were asked how many pets they had. Here are their responses arranged from smallest to largest along with a dot plot of the data. Use the applets to calculate the standard deviation. Let's go to the applets. If you want to be on Canvas, and if you just click the little link that says applets, we can do that. And what we need is we have one quantitative variable single group, but don't click collaborative. So one quantitative variable single group, click that guy, and take those numbers and put them in for data. So 1, 3, 4, 4, 4, 5, 7, 8, 9. We did one quantitative variable single group. Are we okay with that? And then just type that data in and begin analysis. And it'll make a dot plot for us, cool, whatever. This is what we're after, man, all those stats. So the standard deviation, they don't even use those cool symbols like the S sub x and the little sigma. It's SD. So our standard deviation, did you guys get that 2.55 back on yours? Some of y'all might be rounding to 3 decimal places. That's cool. You can set this up to like round however many decimal places you want. So let me go back to my slideshow. The standard deviation is 2.55. Now, to explain its meaning, that's going to take us some getting used to, right? Let me go back to this, though. This is about how many pets these families had. What's the average number of pets that they have, according to the data? What's the average number of pets? What did you guys get? Oh, I got you. 4 is the median, right? What is the average? That's the mean. The mean is the average. So would you believe the average of those group of people that had 5 pets, right? That's a lot of pets. The standard deviation tells you how far they vary from the mean. So this is what we'll write down, and we just got to get used to it. To explain the standard deviation, we'll say that whatever they're talking about, in this problem it's the number of pets, typically varies from the mean by 2.55 pets. The number of pets typically varies from the mean by 2.55 pets. That's what the standard deviation is until we get more used to it. Okay, here's Earl and Kelly's bowling scores. They did all the calculations for us, and Earl's score have a standard deviation of 40, okay? Kelly has a standard deviation of 20. Let's explain each. I will do Earl for us and see if we can do Kelly together, like you in a group. So here's what Earl's standard deviation means. Earl's scores typically vary 40 pins from his mean. So we say standard deviation, we always just talk about, okay, whatever they're talking about varies, whatever that number is, from the mean. See if you and a neighbor can figure out what Kelly's standard deviation of 20 means. What would that mean? Kelly's scores typically vary 20 pins from the mean. So let's try to dive into a little bit of understanding. The standard deviation is not going to go away. I totally know it's new and it's weird. Whose dots in the dot plot are more spread, Earl's or Kelly's? Earl's are way more spread apart, and didn't he have a bigger standard deviation, right? Like his average game, they didn't tell us it, but let's just say his average game is around a 150, then he's going to vary from that by 40 pins. Doesn't he, like, way to the right of it or way to the – he could have a really good game, roll a 190. He could have a really bad game, roll a 110, Like the tighter the standard deviation is, the smaller that is, the more closer you are to your average all the time. So we'll see how that works. Here's 3 facts. Homework questions might ask you about this. Standard deviation is always got to be bigger than or equal to 0. If you had a standard deviation of 0, there's only one time that could happen, and that's if there's no variability whatsoever. So imagine everyone in this room, I know we're not, but imagine everyone in this room was 17 years old, right? I know we're not, but still. Then if I put it all into like a dot plot, you know, and it's like the only score is 17. There is 0 variability, you know what I mean? You know, and so like that's when the standard deviation would be nothing because every stinking data number was the same, right? So that's the only time the standard deviation could be 0. The larger values of your standard deviation means you vary greater, right, from the mean. And the standard deviation, boom, here's the big one, you might even want to circle it, is not resistant. The standard deviation is not resistant. An outlier would drastically change your standard deviation. Like if all of a sudden, you know, like Earl bowled a 300, you know, it's like that's really going to change his standard deviation in that situation, you know, something like that. So an outlier is very, very bad for standard deviation. Cool. And then the last concept of the day is to find quartiles. We're first going to do it by hand, and then I'll show you how it's all done on the computer. So here's some data about the amount of fat grams in 9 different McDonald's filet-o-fish or chicken sandwiches, listed from least to greatest. Quartiles. Help me, guys. I know it's getting boring. Hang with. So the first thing to do to find, like we're going to break this into 4 spots. We're going to break it in half. We're going to find the median. There's 9 different numbers here, right? So the middle term would be, there'd be like 4 on the left and 4 on the right. Would you believe that that guy right there is totally in the middle? So why don't you circle him and put MED underneath that for median. 21 is right smack dab in the middle. Then we'll find the first quartile. You see underlined in pink, there are 4 numbers. Holy crap. Right in the middle of those would have to be like right here. You know, like that, isn't that between the 4 numbers? So you have to average these guys together. If you add 17 plus 19 together and divide it by 2, you know what you get. What's the average of those? 18. Right? Using 18 like right between 17 and 19, you know what I mean? So put a Q1. Guess what Q1 stands for? First quartile. Quartile 1, first quartile, however you want to say it. So the third quartile would be like right here. Isn't there 4 terms on the right side here? The third quartile is right there, and he would be how much? What's 26 plus 28 divided by 2? What would that give you? 27? So it seems like we only broke it into 3 pieces, you know, because we only found 3 numbers, but there are 4 pieces. There's this piece 1, there's this piece 2, there's this piece 3, and there's this piece 4. There's 4 different little spots in between there. That's why they're called quartiles. And 25% of the data will lie in all of those spaces. That's why we split it into quarters. So we'll talk more about that when we make our little box plots next class period. But they say, find and interpret the interquartile range. Well, the interquartile range is real simple. We'll call it this. That stands for interquartile range. Here's how you find it. Q3 minus Q1. You find the interquartile range by doing the third quartile minus the first quartile. This is probably one of the things you will have to calculate. The applet will not do it for you. It will find you the third quartile and the first quartile, but it won't find the interquartile range. So isn't the third quartile 27, right? And the first quartile is 18. So would you please subtract them from each other and tell me what you got? Of course, you can use a calculator, all you need, you know. What'd y'all get? 9. The interquartile range is 9. So what does it mean? A lot of homework questions are going to ask you about that. Here's what that means. The range, because it is a range, of the middle half of the data. The range of the middle half of the data is 9 grams of fat. The range of the middle half of the data. That's what the interquartile range will do. Here is the inside half of the data. Because remember, 25% is here, 25% is here, 25% is here, 25% is here. This is like the low data, this is the high data, and if you put those 2 together, if you go from Q3 to Q1, that's the 50% of the data on the inside, right? So that's the range. What do you think? Would interquartile range be resistant or not resistant? Like if I threw another number way out here, let's just say 53, do you think that's going to affect this inside drastically or not drastically? It's probably not. Like an outlier isn't going to do much to it. It might change some numbers a little bit, but it's not going to drastically change it. So the interquartile range is resistant, right? It is resistant. So, sweet. All right. Let's choose the right measure. There'll be homework questions out of this. What would be the best measure to choose? If the data is skewed or there are outliers, if the data is skewed or there are outliers, we're going to use the median or the interquartile range. If you have skewed data or if there's outliers, the median and interquartile range are the best ones to choose. Like what would be the best measure? And then if you had fairly symmetric or roughly symmetric guys that did not have outliers, using the mean and the standard deviation are good measures. So this is probably a pretty important worksheet. You know how you're going to use it on your tests and quizzes? There's a lot of info on this worksheet about what to choose. Let's do the last couple real quick. 5 adult males were asked their shoe size, and here was the results. Find the standard deviation. Put those numbers into that applet, man, you know. So let's go to the applet and clear out our data. So if you just reset the data. Come on, dude. So reset everything and put that data in. 10, 9, 11, 10, 13. Is that right? 10, 9, 11, 10, 13? Yeah. Standard deviation, did you get 1.517 or something close to that, depending on how y'all's rounded, you know? Cool. So we'll write that down on our worksheet, 1.517. And I'll let you guys choose multiple choice, A, B, C, D. One of those is the interpretation of the standard deviation.